Okay, so far I've talked to you about Indian knowledge systems in the context of astronomy, where we went on a relatively deep dive when we started with material evidence for astronomy, the sources, the texts for that. Then we went on to look at the stories that are containing metaphorical information. From there, we went to mathematical astronomy. We looked at precision, we looked at planetary models, and we saw that there is great development in Indian astronomy from ancient times through pre-modern times. Uh, so now I'd like to talk to you about mathematics. Now, mathematics is not something we can talk about separately from astronomy because these two fields are deeply tied. We saw that mathematics is used in the Siddhanta works and so on. But there are some areas that are distinctly mathematics alone. So some selected connections over time. For example, the value of pi. Pi has been used for so long in archaeology, in architecture, and so on in India. So we find in Baudhayana Silva Sutras, for example, defining pi as 3.114 goes back to the 3rd millennium BC itself. By the time you come to Madhava, he's got an infinite series for pi, the kind of accuracy you get from arctan. You can see this infinite series over here, but this converges rather slowly, right? But it can get you any kind of accuracy that you want. Then by the time you come to Ramanujan in 1910, he had a formula for pi which is one of the fastest convergence series, yielding 8 decimal places with each term that we add over here. So great accuracy in the value of pi coming from Ramanujan's work. So what we are seeing is from Baudhayana's use of pi for altar to Madhava's series for pi to Ramanujan's rapidly convergent series for pi, we are seeing 5,000 years of innovation in the value of pi. So like this, the next thing we can talk about is the series, right? So for example, Aryabhatta, he had got series like 1 plus 2 plus 3 up to n. What is the nth term in the series? Or 1 square plus 2 square up to n square. Or 1 cube plus 2 cube up to n cube. What is the final answer? By the time you come from Aryabhatta to Ramanujam, Ramanujam now has got theorems for divergent series like 1 plus 2 plus 3 up to infinity. He got the answer as minus 1 by 12. It'll be very surprising for us, but he's using convergent values of divergent series to do things of this nature. Very interesting that the amount of intellectual effort in India from Aryabhatta's nth term of divergent series to Ramanujam's convergent values of divergent series, we are seeing a lot of intellectual accomplishments. The third one is in combinatorial mathematics. For example, Pingala. Pingala is dated by Vedavir Arya to 1800 BCE. He enumerates a generation of syllables ga and la like a binary table. If n equal to 1, you can only have ga or you can have la. If n equal to 2, you can have ga ga, la ga, gala, la la. If n equal to 3, you can have this entire truth table over here. This is very similar to what we're doing today in binary arithmetic and computers with truth tables and so on. So we are seeing combinatorics from Pingala to Hemachandra to Ramanujam. Hemachandra Suri, for example, he was concerned with if short beat is 1 beat, long is 2 beats, how many ways are there to arrange short and long beats for n beats? And the answer turns out to be the n plus 1th number in Hemachandra sequence. For example, this is the famous Fibonacci, where if you start with numbers 1 and 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on. And so Hemachandra's answer was you take the n plus 1th number in that series, that is the answer to how many ways can you arrange short and long for n beats. This is a combinatorial problem. And this amazing answer that Hemachandra Suri has given. By the time we come to Ramanujam, we have got partition functions where he's saying, for example, how many partitions are there for 4? It is 5 because you can have it as 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, 2 plus 2 or 4. So there are 5 partitions for the number 4. So Ramanujam had a formula for any number that you take. He's got an asymptotic formula that tells you how many partitions are there. So this is amazing connections of combinatorics from Pingala to Hemachandra Suri to Ramanujam. So what have I shown you here? I've shown that this civilization has been concerned with mathematical things, whether it is pi, whether it is summation of series, whether it is combinatorics. So much of intellectual activity has been expended in getting these answers. And over here in this slide, I want to show you the applied mathematics process in mathematical history. For example, Indians observed some process and they try to understand what this process is using mathematics, physical relationship model using mathematics, or some kind of empirical model. If they didn't understand the physics, they got some empirical model for that. Then they had observations and measurements of the process. We are seeing this in Harappa, Vedanga Jyotisha, various other people like Rishi Kannada, others are using this kind of thing. Then you might have some kind of a model in which you can make refinements, approximations, parameter estimation, and finally get a model for use for prediction and tracking. And over time, even these models will not be correct. So that's why we show refinements over time can be done. So we are seeing Indians have used logical, rational approach by our scientists to identify a phenomena, model its behavior, measure it, refine the model, approximate the process, estimate the parameters, tracking and prediction. All this process is there throughout Indian history. I can show you various processes where this is done. This slide shows application-driven historical growth of math. For example, things like enumeration and counting of objects. We are seeing in Rig Veda itself, where we have numerals, arithmetic, addition, subtraction, multiplication, division, powers of 10. These are there in enumeration, Rig Veda. Then mathematics used for architecture. Example is Baudhayana Sulba Sutra. We are seeing geometry, right angle triangle, circle, pi, square root, and so on. Then mathematics used for commerce. Examples are there in Arthashastra, examples is there in Bakshali manuscript. They are showing how arithmetic, algebra, solving equations are done. Then we are seeing examples of mathematics for modeling the skies. We are seeing trigonometry, spherical geometry, approximation, solving equations. Examples are there in Surya Siddhanta, Aryabhatiya. Then advanced modeling, things like functional approximation, properties, polynomial series, infinite series, solution of equations, algebraic geometry, calculus, combinatorics, whether it's the works of Pingala, Hemachandra, Madhava, Yukti Bhasha, so many people have added to this. What we are seeing is India had a clear historical growth of mathematics with applications, whether it's enumeration, architecture, commerce, modeling, we are seeing evidence of this kind of mathematics. Then in the archaeological record, we can see examples of mathematics in practice. If we go to Harappa, from 3500 BC to 1700 BCE, we are seeing standard weights that have been used. For example, all bricks in Harappa tradition are 4:2:1 ratio, and we are seeing the city laid out in very geometrical patterns, showing how much of emphasis they have laid on geometrical principles, on standardization of weights, and so on. And we have got the famous Mohenjo-daro scale, Lothal ivory scale, Kalibangan terracotta scale, showing that this civilization spent a lot of effort in measurement, making sure that things are standard and such things. This is the evidence that shows that. Then in the Vedas itself, we are seeing evidence of mathematics. For example, the numbers 0, 1 to 9 is found in Rig Veda. And we are finding, for example, there's a positional value number spelt out as 3339, clearly showing place value understanding is there in Rig Veda itself. Shukla Yajurveda has got powers of 10, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6, and so on, showing doubling as a means for understanding this. Then so on, Atharva Veda also has got numbers in it, various numbers, and so on. So clearly we are seeing in the Vedic literature, clear understanding of mathematical principles are there. Then I talked to you in the previous slide about Rishi Atri and the quadrant, how Atri might have used a quadrant, which is a measurement device, in order to measure the angle between the sun and the moon to predict when a solar eclipse would occur. This is noted by Balagangadhar Tilak, who's talking about Turiya Yantra, is what he has used in order to estimate when a solar eclipse will occur. So clearly, Indians also had instrumentation and other things for a very long period of time. And this is the work by Tilak, where he's pointing out what does he mean by Turiya. He's saying that Turiya is also mentioned in Siddhanta Shiromani and other such works. And Atri's eclipse is dated to approximately 4202 BCE or 3811 BC. So at an ancient period of time, Indians already knew models to estimate what an eclipse is all about. They knew that it was the angle between the sun and moon, and as that angle comes to zero, you got an eclipse, and they were able to estimate these things. That is what we are seeing over here, understanding the phenomena, instruments to measure angles, and a predictive capability. Then if we go to the altars described in Taittiriya Samhita, Shatapatha Brahmana, we have got construction of the Dakshina Agni altar. This is the Mahavedi altar, for example, that has got falcon kind of altars and other such things. And sometimes we have got need to increase it 14-fold. If you have to increase it 14-fold, you cannot do it without properties of right angle triangles itself. So Vedveer Arya has estimated that Shatapatha Brahmana and others that are talking about this. I have shown the date for Shatapatha Brahmana from astronomy to 3000 BCE itself. So at least from that time, Indians are aware of right angle triangles, how to use them, and so on. Then the famous Rigvedic Sri Chakra or the Sri Yantra. This is then the Sveteshwara Upanishad. So this is formed with 9 intersecting isosceles triangles, encodes several properties, numerical properties, and so on. This is a very interesting archaeological find where we are finding in Kalibangan, just like today we got mosaic flooring, they had flooring with some kind of a pattern over there. And this pattern is very interesting. It turns out to be a mathematical object over here like I've shown. But what caught my attention is this is also there in Baudhayana Sulba Sutra, this one between 22 and 28, how to construct a square using circles. I've shown that over here, the Sulba Sutra, it talks about how you start with the pivot and the east and west direction, draw a circle with the rope that you have, then intersecting circles, eventually you get this pattern, which is a square and this flower pattern. This is exactly what you're seeing over here in Kalibangan. Therefore, I'm claiming that Baudhayana's time period should perhaps be put the same as this Kalibangan find, approximately 2800 BCE, rather than how the Westerners date him anywhere from 800 BC to 400 BC on linguistic analysis, which is untenable. Here at least we have got an archaeological find that seems to reflect what Baudhayana Sulba Sutra is. Therefore, I say Baudhayana should be in 2800 BCE. Then we are seeing in Atharva Veda, for example, infinity is known in ancient India. You can have infinity in innumerable infinity. The Jain works show infinity in this direction, infinity in the negative direction, infinity in area, infinity in a cube, and so on. So very interesting to see the understanding of infinity. And we have got this in the Brihadaranyaka Upanishad and others, the famous Purnamidam mantra that says, from infinity, if you take away infinity, it continues to be infinity. So clearly Indians had a philosophical understanding of infinity, which is the basis of our mathematical understanding also. So we have talked about a lot of things so far. I've also talked about evidence of Baudhayana Sulba Sutra way back in Kalibangan. We talked about that. We talked about the Mahavedi altar and how if you have to increase the size 14-fold, you must have knowledge of right angle triangles, which Vedveer Arya brought out this particular point. And going forward, we see in Sulba Sutra, for example, square root of 2 computed by what we know today is algorithm equivalent to successive approximation by averaging. And this is also there in cuneiform tablets in the Babylonian collection, 1700 BCE, but they use the base 60 system to use that. Completely different from how Indians have been doing it. Then Baudhayana himself, we have dated him to the time of Kalibangan. We can see that he is in his works in Sulba Sutras, metrology for dimension of bricks and altars, specification of altar dimensions, fractional operations, square roots, pi. These are the kind of things he discusses, including geometrical constructions, squaring of a circle, converting shapes with equal area. Then he also does geometric solution of algebraic problems. If you had to solve a problem, he shows how we can use geometry to solve the problem. Also, alter calculations involving solving linear equations, quadratics, simultaneous equations, and so on. So, Baudhayana clearly in Sulba Sutras, we are seeing a long tradition of geometric ways of doing things. From him, we can go to Apastamba Sulba Sutra, which tentatively, if you think Baudhayana is around 2500 BCE, it's not unreasonable to think Apastamba could be 1900 BCE. Where Baudhayana used geometric proof, Apastamba gave numeric proof to right angle triangles. He presented triples of the Mahavedi. Some of the triples I've shown here, 15, 36, 39, 3, 4, 5. These are all numeric values to the right angle triangle. He had solutions of quadratic equations, simultaneous equations, linear indeterminate equations, a lot of interesting works done by Apastamba. From there we go to Manava Sulba Sutra, which is around 1800 BCE. He's provided several right angle triangle triples. He also found that square root of certain numbers like 2, 61 cannot be determined exactly. It is the basis of our irrational numbers and so on. He also provided right angle triples with fractional sides, things like 2.5, 6, 6.5, 4.5, 6, 7.5. These are all right angle triangles with fractional sides. He approximated the value of pi. He also had arithmetic method to find the largest inscribed square and circle of a given area. These are all mathematical developments we are finding in an ancient period of time. From there we go to Katyayana Sulba Sutra, again we put into about 1700 BCE. So in his work, he declared that this Sautramani Vedi is 1/3 of the Saumiki Vedi. And he gave the triples for that, 5 root 3, 12 root 3, 13 root 3. He provided a method to combine many squares n of length a to form a new square. He also had a formula that today we recognize is the same as the square root formula which Heron used much later in Greece. But this formula is given by Katyayana at a much earlier period of time. Then we have seen Lagada, Vedanga Jyotisha, 1400 BCE text, where he's talking about how to use a rule of 3 again and again, indicating that Indians are aware of a linear prediction of motion using a linear model. We discussed this when we talked about astronomy, where it's equivalent to this form that I've shown. If A by B equal to C by X, X is the unknown. By cross multiplication, we get X equal to BC by A. So this method, Vedanga Jyotisha is saying, apply it again and again to get the result that you want. As an example, if there's a planet, let's say Mars, I know where it is today. 2 days later, I make a measurement. I know how much it has traveled in 2 days' time. Then I might be interested in knowing where will Mars be in 8 days from now. To answer questions like that, Vedanga Jyotisha provides an iterative prediction of motion using a linear model. This is what we find. Very interesting to see this. We have other famous Indian mathematicians, logicians, people like Panini. We don't know the date for that. Westerners put him to around 700 BCE, who worked on algebraic logic to structure of language. Pingala, again we don't know the date. Westerners put him around 700 BCE, who worked on Chanda Shastra, roots of combinatorics. Matrameru, which works on recursive algorithm to find coefficients of the binomial system a plus b to the power of n. That expansion, the coefficients can be got from the Matrameru. Jain literature, where we are talking about Kalpa, Bhagavati Sutras, etc., they talk about infinity, rules of indices, use of logarithms, permutations, combinations. And when you come to Arthashastra, Kautilya's Arthashastra, 322 BCE, we also see evidence of commercial mathematics, rules of taxation, interest, accounting. Very clearly, there is a development of mathematics in India going through very ancient periods of time. If you look at place value arithmetic, Babylonians had a place value system, but they didn't have a zero. Egypt had no place value system, no zero. Greece had no place value system, no zero. In old China, they did not have a place value. In the new Chinese system, they have place value, they got zero. India clearly had a place value system. It also had the concept of zero. So we're seeing that mathematics is greatly refined in India because of clear understanding of place value computations, zero, infinity, and many other computations. So we have covered mathematics in a very ancient period of time. What about mathematics from one current era to 1500 current era? We know Indian numerals have evolved from the Brahmi numerals. Eventually, by the time we come to Gwalior, we're getting the Devanagari numerals over here. And by the time it is exported to Arabia, we're seeing the Gobar on one side, Eastern Arabic. From there, it has gone to the Europe and has become our familiar 1, 2, 3, 4, 5 until 0. So we know that Indian numbers evolved over time and our modern numbers are got from our Devanagari system. And we also know that in the West, they made use of Roman numerals for calculation for a long time until the German called Adam Ries. He wrote in 1522 how to do calculations using Indian numbers, place value. He said is far superior to Latin numerals. At that time, printing press was just invented and his book was printed, and overnight it became a sensation in Europe where people stopped using Latin numerals overnight and started using Indian numerals. The oldest zero, many people didn't know where it was. Some people said it's in the Gwalior temple, some people said it's in Kaimar, in a temple over there. But today we know Bakshali manuscript, which is dated to, carbon dated to around 224 BC, current era, that clearly shows the zero symbol being used. And by looking at the calculation, we can find out that there are many zeros in Bakshali manuscript. We know that the Bakshali manuscript, it was found in around 1881 in Pakistan near Peshawar. A birchbark document with 70 leaves in Sharada script. It was given to Rudolf Hornell for translation. With great difficulty, he put them in order and did a partial translation, and he gave the date of 2nd century. He handed it to the Oxford Bodleian Library in 1902. It was got by a Eurocentric scholar by Kay in 1912, and Kay wanted to disprove Rudolf Hornell's date because he wanted to show that Indians are indebted to the Greeks for their knowledge. So he translated that in 1927, and he proposed the date for Bakshali manuscript should be 12th century. But then he was criticized by several people for saying that is too late, it's got to be much earlier document. This whole thing was revived by Pingree in 1981, and we have had a couple of PhDs on it in 1991 and 1995. In 2017, carbon dating was done on the Bakshali manuscript in Bodleian, and we know that it is dated around 220 current era, settling once and for all this debate of antiquity of this work. And if we take a look at it, it has got, for example, this calculation. This fraction, huge fraction, is multiplied by this fraction to produce this big number. So there are several zeros involved in this, we know that. And moving forward, what are the kind of equations it contains? It is containing simple equations with one unknown. It is containing the same thing that I said about earlier that is there in Lagada's Vedanga Jyotisha. It contains a rule of 3. It contains linear equations with 5 variables, systems of linear equations with more than one unknown, quadratic equations, indeterminate system of linear equations. All these are the kind of things in Bakshali manuscript. Bakshali manuscript, by its own admission, was written by Pandit because somebody contracted him to write mathematics for the use of Vaishya. Around the period of time, 200 current era would make it the Indo-Roman trade. So one can imagine that Indians were learning these kind of mathematics so that they can succeed in the Indo-Roman trade. And the writer of this says he did not invent any of these things. He only says he compiled the knowledge that already existed. That is what Bakshali manuscript was. So you'll notice that what I've talked about in mathematics is very brief because a lot of the Indian mathematics is also used in astronomy. Because of that commonality, I restricted the mathematics content to fairly unique things and fairly short.